All right, so we start off with solving rational equations. And with these, we always want to work on getting a common denominator first. So for number one, actually before we go on number one, let's go with this, common denominator, like that is key. And then the other thing is we need to check our answers. We need to check that whatever answer we get is not one of the domain restrictions. So we need to check the domain restrictions. All right, so let's get to it, finding the common denominator. So for number one, we have x plus 1 and also x plus 7 as their current denominators. And so we really want to just give each other the one that they have. So our second one needs the x plus 1, and our first one needs the x plus 7. Okay, and so the denominator is going to be this common denominator on both sides, the x plus 7, the x plus 1. The numerator we're going to work on so that we can eventually set them equal. So here on the left side, I have that x plus 7 times the x plus 3, and I need to distribute that, kind of FOIL it out. So I have x times x times 3, 7 times x, and 7 times 3. And then on the right side, I have the 15 times the x plus 1. So I need to distribute that, 15x plus 15. And once I have this set up with common denominators on both sides, I want to have this numerator equals this numerator, and then solve that equation. So I have on the left here, just simplifying a little bit as I go, x squared plus 10x plus 21 equals 15x plus 15. And remember, if this is a quadratic equation, if it has an x squared, we want to move everything to one side, get 0 on the other. So I'm going to subtract my 15x over and subtract over my 15. So I end up with x squared minus 5x plus 6 equals 0. And from there, I want to try and factor. So kind of coming up here, I'll just rewrite that. What multiplies to 6 and adds to negative 5? So it multiplies to a positive 6, adds to a negative 5. I have x minus 3 and x minus 2. Negative 3 and negative 2 multiply to 6, add to negative 5, equals 0. And then we set each piece equal to 0. So x is 3 and x is 2. And then we always want to check back, what were those domain restrictions? So initially, when we're looking at our denominators, x cannot be negative 1 or negative 7. So when I get positive 3 and positive 2, those are both good answers because they're not part of our domain restrictions. You could always do the domain restrictions right up front too. We'll do that on this next one. So for number 2, the only domain we have is that x minus 1. So x cannot equal positive 1. Once we go through it, we'll make sure x does not equal positive 1. Okay, so because that's our only denominator, we kind of have 4 over 1. This fraction on the right needs the x minus 1 so that they'll both have common denominators. So here I have 5x over x minus 1 equals 4x minus 4 over x minus 1. And since they both have those common denominators now, I can just set the numerators equal. So I have 5x equals 4x minus 4. And so if I subtract the 4x, when we don't have a quadratic, when we just have x, like a regular linear x to the first, we just can get our x's on one side and our numbers on the other. So here I'm going to subtract the 4x to get my x's together. So I get x equals negative 4. And that is good. X does equal negative 4 because it's not 1. Okay, so the two types of equations we're going to see when we're solving are quadratics that have the x squared in our equation, like this guy, or just the regular x's that we see over on number 2. All right, number 3, we're looking at our denominators. We currently have 5x, 3, and 15x. And we want to build a common denominator that has all of that in it. We want to find a factor, or a multiple of 5x, 3, and 15x. And so 15x does actually contain all that stuff. So we want to give each fraction what it needs to get to the 15x. So first one is 5x. This one needs to be multiplied by 3 on the top and bottom. So I'm going to have 6 over 15x. My second one is 1/3, so the denominator is 3. It needs a 5x on top and bottom. And then the last one already is 15x, so we don't need to change it at all because it already has our common denominator. So now that we have the common denominator, we're looking at this equation with the numerators. We have 6 plus 5x equals 4, and we want to just solve. So subtract the 6 over, I get 5x equals negative 2. So that's the 4 minus 6. And then divide by 5, x is negative 2/5. Okay, check back to our domain restrictions. If our common denominator was 15x, that just means x is not allowed to equal 0. So it is allowed to equal the negative 2/5. So that's our solution. All right, number 4, looking at our denominators that we currently have. We need x and we need x plus 2 as part of our common denominator. So we need to give each fraction what it needs to get there. So the first fraction needs the x plus 2. The second thing is just 3. So its denominator currently is like 3 over 1. It needs the x and the x plus 2. I'm gonna write really small there, but we're going to need to give that whole thing there. And then the last fraction just has the x plus 2. We're going to multiply by x. Okay, so first fraction, we have the x plus 2 times 1, so it's just x plus 2 over x times x plus 2 minus, that numerator is 3 times x, so it's like 3x, and then I'm going to distribute it to the x and to the 2. So I'm going to have 3x squared plus 6x over my common denominator of x and x plus 2. And then equals, I have 4x times the x, so it's going to be 4x squared over that common denominator. Okay, so once we have that common denominator, we can just look at this equation of the numerators. And so I'm going to have the x plus 2. Now be careful here because it's subtraction, so I need to be subtracting both of these terms. So minus 3x squared and minus 6x equals 4x squared. And then, because this is an x squared, a quadratic equation, I want to get everything to one side, 0 on the other side. And so I am going to move everything over to the right, just because I like my x squared term, that coefficient, to be positive. So I'm going to add my 3x squared. If I take this x and this minus 6x, that's really minus 5x. So I'm going to plus 5x to both sides to move that over. And then I have this 2, so I'm going to minus 2 over here. So I really am getting 0 equals 7x squared plus 5x minus 2. And this one we do want to factor and see what comes up. So I'm just going to rewrite up here. 0 equals 7x squared plus 5x minus 2. And this is the AC method of factoring. So I want to say what multiplies to 14 and adds to 5. Sorry, what multiplies to negative 14 and adds to 5. So it's going to be a positive 7 and a negative 2. So I'm going to split the middle. 7x and negative 2x, together those do make the 5x. And bring down my other terms here. Okay, I'm going to group my terms. 7x squared and 7x both have a 7 and an x as factors. So I'm going to factor out the 7x. I'll be left with x plus 1. And then these ones both have a negative 2. So if I factor out a negative 2, I have x plus 1. So totally factoring here, I'm going to have x plus 1 and also the 7x minus 2. And I want to set each piece equal to 0. So if I have x plus 1 equal to 0, then x equals negative 1. And if I have 7x minus 2 equals 0, so 7x equals positive 2, so x is 2/7. And both of these work because if I check up here, my domain restrictions, x can't be 0 and x can't be negative 2. So if I come back to the common denominator, what will make that 0? That's x equals 0 and x equals negative 2. So both of our solutions work here on number 4. All right, number 5. First looking for that common denominator and noticing that on this right-hand side, we have a difference of squares. X squared minus 1 factors to x plus 1 and x minus 1. So together, both of those are going to make that common denominator. And if we want to note right now the domain restrictions, x can't be negative 1 or positive 1 from there. Okay, give each fraction what it needs so that they all have the common denominator. So my first fraction has x minus 1 already. It needs the x plus 1. And my second fraction needs the x minus 1. And my last fraction to the right side has both, so I don't need to change it. So as I go down here, I'm going to distribute that 3. So I have 3x plus 3 over my common denominator plus, and if I distribute the 1 here, I'm just going to have x minus 1 over my common denominator. And then equals 10, because this one I'm just rewriting. It was already in good shape. Okay, so now that I have that common denominator, I'm setting my equation equal of just the numerators. So I have 3x plus 3 plus x minus 1 equals 10. And this one doesn't have any x squared terms, so it's not a quadratic. Instead, we just want to get our x's together and get our numbers together and solve. So here I have 4x plus 2 equals 10. And if I subtract the 2, I get 4x equals 8 and x equals 2. Remember, we already listed our domain restrictions as 1 and negative 1. So 2 works. 2 is the solution. Okay. And then the last of these regular rational functions that we're trying to solve, again, common denominator. And we see on that left-hand side, right-hand side, we get x and x plus 2. This one, when I'm factoring, I just took a GCF of x. And since they both have an x, I pulled that out front. And so I'm left with x plus 2. So you can see that is the common denominator. And so my domain restrictions, x is not allowed to be 0, and x is not allowed to be negative 2. So then let's actually solve. Give each of these fractions what it needs to get to the common denominator. So the first fraction needs an x. The second fraction needs the x plus 2. And the last fraction has both parts, so we don't need to give it anything. Okay, so we have 8x over x and x plus 2 minus, and I am going to distribute this 2 here, 2x plus 2 over the common denominator, and then equals the x minus 2 over the common denominator. And then go ahead with just the numerators. And again, this is subtraction, so I'm going to distribute that minus the subtracting of both terms there. So I have 8x minus 2x plus 2 equals x minus 2. And so over here, I'm going to have 6x plus 2 equals x minus 2. And then I want to get my x's together and my number parts together. So if I subtract x, I'm going to have 5x. And if I subtract 2, I'm going to get negative 4. So x is negative 4/5. And that is not part of our domain restrictions, so it's good. Down below, we have a couple of word problems. Let's read them. Number 7 says, you can kayak around a certain island in 3 hours. Kayaking together, so you'll have help, you and your friend can kayak around the island in 1.4 hours. Find T, the time in hours your friend would take to kayak around the island alone. Okay, so for this one, the one we saw previously, it was, Joe and Sam were painting a house. We had Joe's rate and we had Sam's rate. Well, here we have your rate is 1/3 of the island per hour. Your friend's rate, we don't know. They're asking, what is your friend's, how long would it take? So I'll put like 1 over F, and F is going to be how long, your friend's rate. F is how long your friend would take. And then your joint rate is 1 over 1.4. Okay, so remember how we set this up. Your rate plus your friend's rate is going to be your joint rate. And so that is our equation. In order to figure out the common denominator, we could just multiply 3 times 1.4 times F. And so that is 4.2F is your common denominator. But really, we're just going to give each function what it needs to get there. So when we have the 1/3, that one doesn't have an F and it doesn't have the 1.4. So I need to multiply by 1.4F on the top and bottom. The next one has the F, but it doesn't have the 3 and the 1.4. So times 3 and times the 1.4 on top and bottom. And then the last one has the 1.4, needs the 3 and the F. Okay, so putting that together, I'm going to have 1.4F over the 4.2F, that's your common denominator, plus 4.2 over 4.2F equals 3F over 4.2F. So again, we have a common denominator. We can just look at these numerators. So 1.4F plus 4.2 equals 3F. And so 1.4F, I'm going to subtract from the other side. So subtract on both sides. I get 4.2 equals 1.6F. And in order to solve for F, we're going to take that 4.2 divided by 1.6. And I got 2.625. So it takes your friend 2.625. That's 2 5/8 hours, but it's fine to leave it just as a decimal here, hours, if they were going by themselves. All right, the next word problem has to do with average cost. We saw one with average cost before too. It says the initial cost of a blueprint plotter, makes a big picture of, a house floor plan or something like that. Anyway, this costs $1,500. Each print, it's a lot of paper, a lot of ink, it costs an additional $25. How many blueprints must be plotted for the average cost per blueprint to fall to $75? Okay, so just a reminder, when we're talking about cost and average cost, we're going to say the average cost is the total cost over the number of items. And of course, we're going to need an X in there. And X represents the number of blueprints that we're plotting. Okay, so it says we want our average cost to be $75. Our total cost is going to be the $1,500 plus 25 for each blueprint. So I'm going to say 25X plus the 1,500. And we're dividing by the number of prints. So we divide by X because that's the number of prints. So that's our average cost function there. Then we solve for X. So in this one, I would just multiply by X. So I get 75X equals 25X plus 1,500. and solve for x. So I'm going to subtract the 25x from both sides. So I get 50x equals 1,500. And if I divide by 50, I get x equals 30. So 30 blueprints in order to get to $75 per print. All right, now we're going to switch things up and talk about graphing again. Graphing is section 7.2 of your textbook. Talking about asymptotes and talking about branches of our graph. Okay, we're always going to start with our vertical asymptote, and the vertical asymptote is whatever makes the denominator equal 0. It's whatever is our domain restriction. And so in this case, our vertical asymptote is x equals 3. And so remember that 3, we can plot it on our graph as a vertical line, x equals 3. And we can put it in the middle of our table as 3. Not in the table, but 3 is like the midpoint. So we can choose 2 points to the left and 2 points to the right of that 3. Okay. The last thing that our vertical asymptote gives us here is the domain, that we have all real numbers except x cannot be 3, because that's where the asymptote is. All right. The horizontal asymptote, well, it depends on which type it is. Remember, we have 2 types. We have a type where we just have numbers in the numerator, and we have a type where we have x's in the numerator. And so this one is x. So we're going to look at our coefficients of x in the numerator and denominator. So here I have like 2 over 1. So y equals 2. And that's where my horizontal asymptote is going to be. And my range is all real numbers except y cannot be 2. Okay. From there, we're actually going to plug in the points and get some points for our graph. So plug in 1. I'm just going to kind of do it to the side here. So I have 2 times 1 minus 1 over 1 minus 3. So I'm plugging 1 into both x's there. So in the numerator, I get 2 minus 1, which is 1. In the denominator, I get negative 2. So I have negative 0.5. If I plug in 2 to my function, I get 2 times 2 minus 1, which is 3, over 2 minus 3, which is negative 1. So 3 over negative 1 is negative 3. And I'm going to go ahead and plot that. So positive 1 comma negative 0.5 is right there. And positive 2 comma negative 3 is there. So we see our first branch here going through those points and close to those asymptotes. Okay, continue with my other 2 points. So plugging in 4, 2 times 4 minus 1, so 8 minus 1 is 7, over 4 minus 3, which is 1. So 7 over 1 is 7. And then plugging in 5. 2 times 5 minus 1 is 9. And then 5 minus 3 is 2. So 9 halves is 4.5. So we plot those last 2 points, 4 comma 7 and 5 comma 4.5. And draw the second branch of our graph. All right, number 10 is similar, except it's going to be the other type where we find our horizontal asymptote the other way. So starting with our vertical asymptote, we're looking at the denominator. And we're saying negative 4 would make that 0. So we're going to have our asymptote at negative 4. I'm going to put the negative 4 on the graph, put the negative 4 in the middle of my table, and have my domain all real numbers except x can't be negative 4. For my horizontal asymptote, because this is not x's on the top, it's just numbers, a constant on the top, we're going to look over here at the plus 3 for our horizontal asymptote. So y equals 3. And our range is all real numbers except y cannot be 3. Okay. When we find points for our table, since our asymptote there was at -4, I'm going to go 2 to the left, -5 and -6, 2 to the right at -3 and -2. I'm going to plug those in to my function. So I have -1 over -6 plus 4, and then plus 3. So I have 1 over -2, sorry, -1 over -2. So that's 1/2 plus 3. So it's 3.5. Okay, plugging in -5, 1, and I have -5 plus 4, so that's -1 over -1, that's +1, plus 3 is 4. And if I go ahead and plot those points, I'm kind of running into it here, but -6, 3.5, and -5, 4. And so my branch is going to be up here, staying close to my asymptotes, but not crossing over. And then plugging in my last 2 points here, -3, so 1 over -3 plus 4, and then plus 3. So for that fractional part, -1 over +1, so that's a -1 plus 3 is 2. And then my last one, when I'm plugging in that -2 on the bottom, I get -1/2 plus 3, which is 2.5. Okay, so I'm going to have -3, 2, and -2, 2.5. So getting close to those asymptotes there. Okay, so that's what graphing is. And this is graphing when I just have that simple rational function. There's no holes on these. Remember, holes come whenever we have a factor that we cancel on both the numerator and the denominator. So that's what we're asking for down here. It says identify the equations of any asymptotes and the coordinates of any holes for each function. So we first want to start off by factoring. And number 11, factoring both the numerator and denominator, we have a GCF of x. So I have x and x plus 5 in the numerator, and x plus 1 in the denominator. So if I reduce, I can reduce an x on the numerator and denominator. And because that's an x, that's really what our value would be 0. So it's going to be 0, comma, something will be our whole. Okay, and we're going to use this simplified version to find what y value it is. So once I know it's 0, comma, something, I can plug in 0 into this simplified function. So plug in 0, 0 plus 5 over 0 plus 1. So it's just 5 over 1, which is 5. So 0, comma, 5 is where the whole will be in this equation. Okay, the vertical asymptote is going to come from the bottom, the denominator there, and so it's going to be x equals -1. And the horizontal asymptote, because we still have x's in both the numerator and denominator, we're looking at like the coefficient of those x's, so it's like 1 over 1, y equals 1. All right, let's try number 12. Same thing, we want to factor both the numerator and the denominator. So that numerator is the hard factoring. Take your time, do it right. Let's factor it. So I'm going to kind of go down here below. If I have 2x squared minus 5x minus 3, I'm saying what multiplies to -6 and adds to -5. And so this one's going to be -6 and +1. So I have 2x squared minus 6x plus 1x minus 3. These first two terms have a 2x in common. And I'm going to have x minus 3 left. The second two terms just have a 1 in common. And I have x minus 3 left. So I get x minus 3 and 2x plus 1 as my factored portion here. So in the numerator, I'm going to have my x minus 3 and 2x plus 1. In the denominator, we're also factoring. We're saying what multiplies to +3 and adds to -4. And that's going to be -3 and -1. Okay, so whatever values are the ones that cancel, that is where our whole comes from. So so the x value is going to be 3 comma something. And remember that something comes from our simplified version. So if I plug in 3 to that, 2 times 3 plus 1, that's 7. And then 3 minus 1 is 2. So 7 halves, or 3.5. That is the coordinates of our whole. Vertical asymptote is coming from what's left in the denominator. So x minus 1 tells us the vertical asymptote is x equals 1. And our horizontal asymptote comes from these coefficients of our x. 2 over 1, so y equals 2. All right, the last type of question we're going to have here is writing our own equation given where the asymptotes are, where there's holes, if there's holes. So for number 13, it says, write the equation of a rational function with asymptotes at x equals 4 and y equals 2. All right, so remember, when we're writing in our equation, whatever is the x asymptote or the vertical asymptote is what makes the denominator equal 0. So if it's 4, we're going to have x minus 4 in the denominator. For the y equals 2, this tells us that either the coefficients of our x over, like numerator over denominator, are going to be 2, so like this, or if we just have a number in our numerator, we can have a plus 2 at the end. Either one of those still gives the same type of asymptotes. All right, last one, number 4, we're doing the same thing except we have a hole. So looking first at our asymptotes, x equals 0 just tells us we have an x in the denominator. If we have a hole at 2, we're going to have x minus 2 on both the top and the bottom, because that's going to have to cancel. And then the y equals 0, you can either have a plus 0 there, or as long as you don't put any extra number up top, you are fine. And so that is going to give us 2 comma 1/2 as our whole.